Sea level seems like a pretty easy concept, right? You just measure the average level of the oceans and that's that. But what about parts of the Earth where there aren't oceans? For example, when we say that Mount Everest is 8,850 meters above sea level, how do we know what sea level would be beneath Mount Everest, since there's no sea for hundreds of kilometers? If the Earth were flat, then things would be easy. We'd just draw a straight line through the average height of the oceans and be done with it. But the Earth isn't flat. If the Earth were spherical, it would be easy too, because we could just measure the average distance from the center of the Earth to the surface of the ocean. But the Earth isn't spherical. It's spinning, so bits closer to the equator are thrown out by centrifugal effects and the poles get squashed in a bit. In fact, the Earth is so non-spherical that it's 42 kilometers farther across at the equator than from pole to pole. That means if you thought the Earth were a sphere and defined sea level by standing on the sea ice at the North Pole, then the surface of the ocean at the equator would be 21 kilometers above sea level. This bulging is also why the Chimborazo volcano in Ecuador, and not Mount Everest, is the peak that's actually farthest from the center of the Earth. So how do we know what sea level is? Well, water is held on Earth by gravity, so we could model the Earth as a flattened and stretched spinning sphere, and then calculate what height the oceans would settle to when pulled by gravity onto the surface of that ellipsoid. Except the interior of the Earth doesn't have the same density everywhere, which means gravity is slightly stronger or weaker at different points around the globe, and the oceans tend to puddle more near the dense spots. These aren't small changes either. The level of the sea can vary by up to 100 meters from a uniform ellipsoid, depending on the density of the Earth beneath it. And on top of that, literally, there are these pesky things called continents moving around on the Earth's surface. These dense lumps of rock bump out from the ellipsoid and their mass gravitationally attracts oceans, while valleys in the ocean floor have less mass and the oceans flow away shallower. And this is the real conundrum, because the very presence of a mountain and continent on which it sits changes the level of the sea. The gravitational attraction of land pulls more water nearby, raising the sea around it. So to determine the height of a mountain above sea level, should we use the height the sea would be if the mountain weren't there at all, or the height the sea would be if the mountain weren't there but its gravity were? The people who worry about such things, called geodetic scientists or geodesists, decided that we should indeed define sea level using the strength of gravity, so they went about creating an incredibly detailed model of the Earth's gravitational field, called creatively the Earth Gravitational Model.